Hi, and welcome to our video. The future will be an exciting time, especially as machine learning, AI, and autonomous electronics begin to facilitate scientific achievement. Such achievements would invariably help us push the boundaries of space exploration and medicine, and silicon wafers will partly be the reason for such advancements. Wafers are thin slices of semiconducting material found in virtually every device, such as your laptop or smartphone. And wafer preparation is therefore of paramount importance. In this video, we discuss an industrial wafer preparation process in our attempt to control that process with a PID controller. So let's get started. Chemical mechanical planarization is a polishing process which utilizes a chemical slurry formulation and mechanical polishing process to remove unwanted conductive or dielectric materials on the silicon wafer, achieving a near perfect flat and smooth surface upon which layers of integrated circuitry are built. A 1999 study by Wei Su Sang and colleagues highlighted that the Preston equation is heavily utilized despite it being purely empirical. They also noted the nebulous definition of velocity, saying that in an orbital CMP system, the carrier and pad rotate at their respective speeds, and the velocity varies from wafer center to edge during polishing. In other words, defining velocity is a little bit complicated. In the same study, two modified equations were shown to be superior in matching empirical evidence. Regardless of these facts, we decided to create a controller for the original Preston equation because it could serve as a starting point for more complicated controllers. In the original Preston equation, the P is the piston pressure, which will hold constant in our system, and we'll assume that V is the velocity of the tray.
The general process for creating a PID controller boils down to the following: using experimental data or implementing a first principles model to generate data that is then used to generate FOPDT parameters. Finally, using those FOPDT parameters to yield PID tuning parameters. In our case, the original Preston equation served as our first principles model, even though we mentioned that it is purely empirical in nature. Regression analysis was applied to generated data to produce tuning parameters. The process data that was created is shown in the black line and demonstrates the machine running at 30% and then at 50% of our possible velocity, 0 to 35.9 meters per minute being the full range. The negative Kp makes physical sense because if we increase the CMP velocity, then we expect the wafer thickness to decrease. Thus, there exists a sort of inverse relationship between controller output and the process variable. Keep this in mind.
We then used the FOPDT parameters and used IMC correlations to produce our PID tuning parameters. However, upon plotting our controller and the system responses, we noticed that the desired inverse relationship was not showing up. We tried a plethora of tuning combinations and still to no avail. A colleague of ours noted that our system was an integrated system, meaning that it never reaches steady state, as long as the controller continues to input signals. For example, a water hose filling up a bucket will never reach steady state because it will continue to overfill indefinitely. Contrast that with a thermostat that will increase the heater output until the desired temperature is reached. For our controller, this meant that a PID should be replaced with a P-only controller. The final KC tuning parameter used was -1. The final result of the closed-looped control is shown here. The PI-only controller performs just the way we want. Specifically, there is no overshoot of the set point. Again, this is important so that we don't lose the wafers that are being produced. Because our system responds in a similar time frame as other CMP systems, this lends credence to our simplified model behaving as expected compared to a more robust model.
Current methods measure the thickness before and after the process because currently it is the more accurate method to measure copper layer thickness. In the future, improved real-time thickness detection would allow better use of a P-only controller. Having a closed-loop CMP controller would allow for a more consistent yield and thus improve wafer production. Another avenue of exploration would be implementing the modified Preston and Singh equation in the P-only controller to mirror the empirical evidence more closely.
Compared to a more robust model. I need to do it again.
Yeah, just go for it again.
I don't have to restart it.
No, you're good. Just keep reading.
It's really bad.
It's okay.
I keep on speeding up and slowing down and speeding up and